In the next subsection, we finally put this all together for parallel sorting algorithms that use all these primitives that we've built up and go much beyond what we've seen initially for parallel string matching, where we could get away with just these very simple tricks of parallelizing. This time we'll have to try a little harder, but the algorithms that come out are much more interesting. We'll look at the two key algorithms we discussed in Unit 3, Mergesort and Quicksort. So let's look at Mergesort and think about how can we do what Mergesort does in parallel, doing it on our PRAM. One thing that's easy, Mergesort, remember, divide and conquer and all that, it had these recursive calls. You first sort the first half and then the second half, and then you merge the result when these recursive calls come back. Because the two recursive calls work on a disjoint part of the input, you can just keep them running in parallel. And we will express that pretty much like that. That's the easy bit. The bulk of the work in Mergesort, of course, is in merging. And if you think about it, just the very last merge, the merge that you do at the very end after the two first recursive calls came back, already takes linear time. It has to go over the entire input once. If you parallelize everything before that perfectly, but then this last bit is sequential, you're still at linear parallel time. And so that's hardly better than the n log n time we started with. In general, for PRAM algorithms, your goal should rather be something like logarithmic to a power, or log to the 5th power if you want to go crazy, or something like that. That's a good algorithm. Maybe square root n if you can't get down to log or polylog. But linear is not so great if you started from n log n. So if we want to go beyond that, if we want to go faster than, well, have more parallelism than that, we have to somehow tackle the merge part as well. We have to do that in parallel. And the method I've shown you seems completely unhelpful for that. And the solution will be to solve the same problem, but look at it from a single element's perspective, and then try to do all of that in parallel. That's more versatile than just this application. You can often do that, and it's often helpful also for other kinds of programming. So I think this is a good way to practice thinking of this way. It often leads to more scalable algorithms in a more general sense than just PRAM. For our merging procedure, we can say for every element, it's either in the left or in the right run initially, and we have to find its position in the final merged sorted run. And it turns out that this position can be computed relatively easily as the sum of two things. First of all, it's the position in the sorted output. That's the same as its rank. We've used that terminology before. It's the number of elements that are smaller. That coincides with the position in a sorted array. And there's two types of elements, those that come from the left run and those that come from the right run. And we can just count how many are small in the left, how many are small in the right, add that up. That's your rank in the sorted output. So we can do that easily for one of the runs, namely the one that contains x. That run, as the name says, is sorted. So the position of x there already is its rank within that run. And for the other run, we can use another algorithm to find the rank, and that's binary search. All the way back, Unit 2, we've covered it all. Binary search is just a way of finding, in a sorted list, how many elements are smaller than some other element. Right? You start in the middle, are you bigger, smaller, and so on. You wiggle your way through. And so you find the position where you would have to insert this element if it's not already there, so that the list remains sorted. And that's, again, the rank of this element. And if we have both of these information pieces collected, we can just add the two positions up and move the element there in a second round. OK? That's pretty much it. Here's what this looks in code. Is It's a little intimidating by the size of it, but all the individual parts you have either seen or they're what it was on the last slide. The overall recursive scaffolding for merge sort is as we had it before in the sequential algorithm. You first recurse in the two halves. And note here I used a different construct that we haven't seen before. I didn't want to cross it out. I'm just writing, do these two things in parallel, which means in more low-level PRAM code, you would have to assign somehow two processing, you would have to distribute this to different processing elements. For sorting, I think it's usually sufficient to think of each position in the array having its own little processor attached to it. And so doing this in parallel would just mean the left side is handled by its processors and the right side by that side's processors, and they can work independently. Then we invoke the parallel merge that we'll discuss in a second. And what's left is to copy back our merge method. Also, the sequential one from unit 3 was merging from the runs into an output buffer. That's why we always pass this second array buffer around. So after merging is done, we have to copy back from the buffer to the array that we actually want the sorted list to be in. And we can do that in parallel as well. Easy. Every processor takes care of one position. That was the easy part, right? That's almost as we had it before, with 2 times in parallel sprinkled in. The interesting bit is the merging. And remember from the last slide, we have to do 2 things for each element. We have to find its position, and then we have to get it there. The first phase, finding the position, is split up in the elements that come from the left run and the elements that come up from the right run, but the 2 phases are intermingled. It was shorter to write it in that way, so you don't need an extra array for storing the target addresses. So this first one is for the elements in the left run. So you do a binary search with your element. And again, we do this in parallel. So every processor does this for its element, does a binary search in the right run. That returns the number of elements that are smaller in that run. And we add the rank in the left run. So R at the end of this is the position where the element should go in the sorted output. And so as a second step, we just write it to that position in the buffer. That was for the elements that come from the left run, and the one for the right run is the same. It's just symmetric. You do a binary search in the left run, and you add the rank in the right run. But the moving to the buffer part is the same. OK? I wanted to show the detailed code for this because I think it's fairly elegant using these constructions in parallel. It doesn't take a lot of code to write all these things out. And there's no really nasty bits needed in this. OK? Any questions on this so far? Let's have a quick look at how well this does. And maybe we should do this in the code. So again, what did I use for colors in the past? Maybe you need to stay consistent. All right, green is time. So if we go to merge, then the binary search is done sequentially, right? I'm not trying to parallelize the binary search, and I don't think it's easily possible. I'm not aware of a speed up for that part. Because binary search, it very much needs to know what the comparison outcome was to decide where to go next. That's a data dependency. It's not easy to overcome that. So that part will take linear time, logarithmic time. logarithmic in the size of the run that we're working in, but I'm just rounding that up to n generously because it's never longer than that. The rest is all linear, is all constant time. And we're doing all this in parallel. And same here. So we have 2 times log n for the merge as parallel time. That's this part. Then merge sort itself is a little more tricky because it is this recursive procedure that calls itself. But you can do a simple argument about the recursion tree. So we start with the entire list, and we cut it in 2 halves. Okay, almost like 2 halves. A recursively cut, and so on, until you're eventually at individual elements all the way down. And you can argue the height of this tree is roughly logarithmic. That's this height. And on each level, we need to add up these log n cost from merge. But we have to do those. Yes, it's at most log n. Some of the merges are cheaper than that, but half of them need a constant times log n. So it's correct that most merges need theta log n. And so the total time is, on each level we have to wait log n time, and we have log n levels. So it's log squared time, parallel time in total. Now for work, if we go back, it's easy in this case because we don't use any building blocks. We just have to multiply this, what happens inside the loops, with how many times we do the loops. So this merging procedure has n log n time, and that's just done twice. So because of the binary searches, this is not work efficient for merge. We know the normal merge ran in linear time, but now work has gone up from n to n log n. But what we were winning from it is that the parallel time goes down to log n. Again, if you sum this up over all the levels, you can basically just multiply by log n by the height, and you get this bound of n log squared n work. Okay? So is that good or bad? It's much faster in terms of parallel time than any of the sequential algorithms, or the simple version where you only recursively sort things in parallel, but then the merge is sequential. Because that still had linear time, and now we're exponentially faster in the parallel time. So if you have many processors, it's definitely better. The work went up a little bit, a log factor, which you may or may not feel. That depends a bit on the number of processors. Now, there is a way to make the merge procedure that I've shown you work efficient, but it's quite tricky and involved. So this is again just for your curiosity. The key idea is something like a blocking trick again. You don't do the full binary search for every element, but only for some of the elements. And you know, for the other elements, their rank must be sandwiched between whatever the next elements are where you did the full binary search. Now that alone is not enough, because you could still have a huge range for some of the elements to search. So it's a little more tricky than that. But that's the idea. You could try to not do the binary search for all elements. But the beauty of this simple code is definitely lost in that process. So if you want a work-efficient parallel sorting algorithm, with merge sort, it's not so easy to get there. Fortunately, we have another sorting algorithm. Let's also try our luck with Quicksort. First of all, the overall structure is the same. It's a recursive algorithm, and the two recursive calls are on completely independent bits of the data, so we can do those in parallel. That's the easy part. And again, if we only do that, it's not much use. We still have the first partitioning round that spends linear time sequentially. Unless we parallelize that, no good speedup is possible. And our code that we've had in Unit 3 for the fast sequential partitioning method is not going to cut it here, because it very much depends on the previous comparisons, how the pointers move and all that. So again, we have to switch perspective to a per element point of view. And so here it's a little trickier than in merging, I think, but overall a bit more elegant maybe. You split, again, the partitioning process into several phases. A reconnaissance phase where you collect information, and then a second or a last phase where you act on that information. And what is the information in this case for partitioning? We just need to know for each element if it's smaller or bigger than the pivot. So it's a single comparison, no binary searches or something like that. But then from that single comparison, you don't already know where you have to go in the final array, because that depends on all the elements before you. But if you think about that, that's exactly what prefix sums can do. If you're in the group of small elements, you need to know how many small elements are before you to the left in the array. And that's precisely what prefix sums can do for you in decent parallel time. Not constant time, but we've seen logarithmic time. Okay, let's try to also put that in code. The recursive scaffolding is, as before, is even closer to the original code for Quicksort. The only change here is this in parallel. The partitioning method is a little more different. We pass in again. So you remember, for Quicksort, it's important to choose a decent pivot element. And so all that we've discussed previously about how a pivot can be chosen well, or how to improve on this, that's encapsulated in this choose pivot method, and the same tricks can be played as I've shown in Unit 3. So don't discuss that again. So we have this position of the pivot that we pass down. And so as a first step, we swap that out of the way. Now for all the other elements, that's the first phase here, where we collect information. And this time we don't get around without storing some information in between. So we have this array S, which contains, I think it's S for smaller and L for larger. These two arrays store, is an element smaller than the pivot or not? And so, okay, I'm using this Iverson bracket. So this square brackets around a condition supposed to mean 1 if the condition is true and 0 if the condition is false. It's just a shorthand. So we do the comparison and set small accordingly, and large is then just the opposite of that. We can do that in parallel for each element independently, because it only depends on the pivot element and this element. Then we have these two arrays, and then we compute the parallel prefix sum of those two. Because precisely, again, if I'm in the small cohort and I'm the fifth element from the left that is small, I have to go to position 5 at the very end. In the large cohort, it's similar, but I have to add the offset of how many elements are in the small group to that. So first of all, we just compute the parallel prefix sums. Then we also compute how many elements are small in total. That's J. That will be the position of the pivot. And then we can again work in parallel for the second phase, for moving moving the data where it belongs. And here we do the comparison with the pivot a second time, because that's the most convenient way to know, is my element, is that a small one or a large one? I've forgotten if I haven't saved it. So the cheapest way is to just look, do the comparison again. So if I speaking is processing element I, if I'm responsible for element AI, I check again. If I'm small, then I look up in position S of I where I'm supposed to go. And if I'm large, I'm looking up in L of I, but I have to add this offset J. This I'm off by ones, like you have to subtract 1 here because we start arrays at 0 and all that again. I hope that the code is correct with respect to all those details. So again, that's the moving phase. And that can all nicely be done in parallel. Okay, is the code somewhat clear? Let's have a brief look at how good this is again. So for the time, if you look at all of those loops, they're all in parallel. So we only have to look inside one of those. And that's constant time. It's just a single comparison and a few memory assignments. And same thing here. That's also constant time. Just a few comparisons and a few read and writes. There's, of course, the parallel prefix sum, which is not for free in terms of parallel time. That costs us log n parallel time. So the overall partitioning procedure, if you look, the rest, that's constant time, that's constant time. It's all constant time except for the prefix sums. So the overall time for the partitioning phase is log n again. And then if we do a similar trick for the analysis as for merge sort, if we need log n time on each level of the partitioning step, then we can multiply that with the depth of the recursion tree. Now the recursion tree in Quicksort is not quite as rigid and clearly balanced as the one in Mergesort. It's only in expectation so. But I don't want to go into this in more detail. I will just use the expected depth and say the caveat here is that this is expected case only. So you don't get easily this worst case bound from Mergesort. For that, you would have to pick a really good pivot, which gets us into the trouble of how to find a good pivot. And so I don't think that's easy in parallel. But the expectation bound is fine. And so we get the same result as for Mergesort, log squared parallel time. The difference is in the work, because if we look back in terms of work, all those loops, they're just doing roughly n times some constant operations. So that's linear time, linear work, sorry. The same here. We also have the parallel prefix sum. And now it depends which method for that you use. But we know there's a way to do it work efficiently with linear work. So I might as well use our good algorithm instead of one of the poorer ones. And so the overall work is linear in this case. And remember, that was not so easy for Mergesort. The merging step was also log n parallel time, but n log n work in the version that I've shown you. And that means Quicksort in total, if you again multiply with the expected depth of the recursion tree, you get n log n work. And we know that that's the best in the sequential world as well for comparison-based sorting. So we're work efficient. That was not so easy to do with Mergesort, but Quicksort gets it here, at least in expectation. Now you could ask, is this the best you can possibly go for? For all the natural methods, we seem to arrive at this parallel time log squared n. Is there something magic about log squared of n? Or log n squared, I should say. So this is the typical notation. I don't know if this causes confusion, but what's meant is log of n and then a square, right? It's not something like log of n. sometimes also written with a superscript. Log n to the power 2. Is there something magic about log squared? There's nothing magic about log squared. If you're willing to go to more sophisticated methods, you can actually get down to log n parallel time. It's some intricate variant of merge sort, but what you have to do for that is basically give up the nice separation of, now I'm doing this merge step. When I'm done with that merge step, I'll do the next merge step higher up in the recursion tree. You have to break that all open and kind of start parts of the next merge while you're still finishing off parts of the previous merge. By interleaving things that way, you can improve the overall parallel time. It's a pretty cool theoretical result. I'm not sure if this is realistic to ever be implemented and be competitive. But it's in theory possible to cut it down to logarithmic time, parallel time, and potentially faster on these other variants of the PRAM where you can do concurrent writes. That's one side of the things I just wanted to mention this result without giving you any details. That's beyond the scope. The other part in practice, if you want to implement algorithms, we have to deal with the fact that these things are not PRAMs with these nice synchronized processors where synchronization is basically free. So the practical challenge is to do what we've done, but not break things down into tiny little work packages. And so it's often more convenient to structure code a little differently. If you want to see some really neat and fairly recently designed examples, the Java library has a few that are really nice and well readable, and nothing too crazy in the code there. But they're in a way close to our parallel merge sort, just different way to slice up work packages. All right. I think that's just another way of saying if you were to implement a complicated algorithm that has log n parallel time instead of log squared for the simpler methods, to see that difference, you need a lot of processing elements. Otherwise, the work will dominate. Remember Brent's theorem to convert from work and span to actual time if you have a fixed number of processors. And because here work is still n log n, you need a fair number of processors before that difference between log squared n and log n makes its way through to the final result.